Just to explain the music, it's a Beethoven triple concerto. There's, you can hear a violin, cello, and piano. Well, the connection here is that we're going to be dealing with cross products, like force equals V cross B. So we have three vectors that we have to deal with, and makes life a little bit more complicated. So it's here's the piano. Okay. So remember that in cross product, you're dealing with three perpendicular vectors, or the perpendicularity of the vectors. So, very good. Let's get going with this subject of magnetism. Now, what we said was that we knew about magnetic materials for millennia, but it wasn't until 1820 that it was discovered that magnetism and moving electric charges interacted with each other. That was the famous discovery of Ørsted. What we did, we demonstrated it. He simply started with a battery, grâce à Monsieur Volta, and just passed it through a wire, probably had a resistor in here, and he just passed current through, and he noticed that a compass needle moved. Now that was the connection between a current and some kind of magnetic effect. Okay, now, in hindsight, can you imagine what this could be good for? I suppose that happened to you. Would you say, "Oh, that's nothing"? No. But can you let's see? Can you think of a quick application for starters? No? Yes. Orientation, yeah, maybe. How about signaling? Suppose I have my voltage and I put my wire 500 miles away and I put a compass needle over here. And I open and shut a switch. I open and shut a switch and send the current, and the magnet jiggles 500 miles away, almost at the speed of light. Goodbye, Pony Express. Right? I mean, that's fabulous. Instantaneous communication. You make up a code, Morse code, dot, dot, dash, dot, dot, dash, so on. You got instantaneous communication. It's fantastic. How about making something move? Suppose I have a mill or something. I want to grind corn. I could on and off the current and make that compass. If I can make the thing strong enough, I can make the needle go back and forth and maybe grind something. Got a little bit of a motor there. Takes away muscle power or horsepower or water power. See, this is just the beginning of fantastic things. So the telegraph, of course, was an immediate application. And already, this was 1820, by 1850, 60, say the Civil War. I don't know if you've ever seen a Civil War movie, but right, first thing they do before they attack is the cavalry goes out and cuts the telegraph lines, right? So they can't signal to each other that the Yankees are coming or the Confederates are coming. So this is already by 1860, there were telegraph lines stretched from place to place so you could signal back home, get information, and so on. Send telegrams. So that's just the beginning, of course. Now, I have this little joke thing, which I think I put in your thing, and that is this lady says, I'm overweight because the fillings in my teeth are attracted to the magnets on my door, on the refrigerator door, so I'm pulled to the refrigerator, and so I'm overweight. The point of that little joke is that very few things are really magnetic. We have a few things like this particular material that's made of there, and we have a couple of magnets over here, but most things aren't. Like aluminum is not, copper is not, silver is not, gold is not, this table is not. Most things are not magnetic intrinsically. Of course, you can pass a current through a copper or gold, so you could create magnetic influence, but most things are not. So some people confuse if a thing is a metal, it's magnetic, or if it's magnetic, it must be a metal. That isn't even true. Actually, it turns out that most metals are not magnetic, that is ferromagnetic, permanently magnets. And in fact, not all ferromagnets are metals. For example, the tack magnets that you put under, the kind of black, they're not even conductors, they're insulators. So you have insulating magnets. In fact, the strongest magnets we know are rare earth magnets, and they are not conductors. So you can have materials that are insulator, but they nevertheless have magnetic material. What's going on inside them? Yes, there are actually electric currents creating the magnetism, but they're bound electric currents. They're kind of little spinning currents inside atoms and nuclei. Well, for ferromagnetic materials, it's the electrons that are going around in loops and producing the magnetic fields inside the material, and that leaks out. So, but they don't have to be conducting electrons. You don't have to have conducting electrons to make strong magnets. The very strong magnets, in fact, this is a whole big issue now. Some of the strongest magnets use what's called rare earth elements. You may have come across them in your chemistry. One of the rows is a rare earths, samarium, terbium, things like that. They make the strongest magnets. Not stronger than iron even. And that's a big issue because those elements are relatively rare, and a lot of them are in China, so we have a little bit go around with China about importing rare earth metals, because they're used in conductors in the magnetic properties used in magnetic memories. So they're very valuable commodity. So anyhow, we know very well that magnetic poles, as I showed you here, affect other magnetic poles. This is one permanent magnet, and there's another permanent magnet, and these poles affect each other. That's well known. But of course, this was the big breakthrough where we had the electrification. Now, the important point, though, is that we always get a north and a south pole together. This is a very important idea. Whereas with electric charge, we have plus and minus, and you can get separate electrons. For example, I'm going to show you later where we create electrons in this tube, and we can shoot them across. And if you want, you can collect them, and you can separate single electrons. In fact, there was an experiment once where somebody trapped a single electron in a magnetic bottle, one electron, and he kept it there they just experimented on it. They did these long-term experiments on it. They even gave it a name. I think they called it Charlie. They go in the morning, and Charlie's still there? Yeah, he's still there. So, this was at the University of Washington. The guy won a Nobel Prize for this experiment. He was able to study the properties of one electron in isolation. Really remarkable experiment. And so you can do that, and you can separate charges. Like you can get protons. You can take the hydrogen, you tear off the electron, you're left with the proton, and you can deal with the protons separately. So those are called monopoles, single poles. Electric monopole is ordinary. Turns out, though, that we have never found a magnetic monopole. People have searched for a long time, theorized about them, but there is no, yet, magnetic monopole. So these are your electric monopoles. So we just don't find a north. If you look at this thing, there's a north and a south. There's a north and there's a north, there's a south. Every magnet you'll ever come across will have a north and a south. If you find an isolated north, go to Stockholm and collect your Nobel Prize. As we know, you can put, for example, with one of these magnetic things where you do have north-south, and what we do is we put iron filings, and you see them sort of go out in kind of patterns. So we say that the lines are coming out of the north and go to the south. Well, maybe this, yeah, okay. That's a convention, sort of like the same convention that we made up for the electric monopoles, where we said the lines would come out of plus charges and go into minus charges. Difference is you could have a plus charge isolated and you just have lines going out without even having a minus charge nearby. So that's a very important distinction. And this is just a funny thing. This was a brush that was supposed to remove lint, and it says on it, this has magnetic action. No, what it is the same kind of electrostatic thing that we used early on, where you rub something and it picks up charge. So you may make a distinction between electric and magnetic. Most things, like if things stick to you, it's probably not a magnetic effect, because magnetism is more scarce. But electrification by friction can happen almost anywhere. So you'll see this confusion, people confusing electricity and magnetism. Although there is a deep connection, which I hope we'll get to. But at this level, we're going to say they're different. And this was the great experiment of Ørsted. And the thing is that the static charges don't interact with magnetic materials or magnetic poles, but the currents do. And there's a famous experiment by this man Ampere, after whom the current unit is measured, where he had current going through parallel wires, and when the currents were going one way, they attracted you. If you could make them go the other way, they would repel. So he was showing that these moving currents, these moving charges, currents, produce magnetic effects one upon the other. Both wires became magnets and were attracting and repelling each other. And this one, I think I'm going to pass this up. You can look at it. It's going to be kind of like the demo I'm going to do later. So all it shows is that if you have a coil with current in it, it also attracts permanent magnets, which you wouldn't be surprised at this point. Now, as I tried to say at the beginning last time, we follow the same pattern that we did with electricity for magnetism. You can find very similar analogs for the magnetic fields and charges with all we've learned about electricity. So if you remember one, you can transfer that pattern with some changes to the magnetic effects. The difference is that, as I said here, you're going to run into a lot of right angles. And so you have this triple effect, three things. For example, in the Biot-Savart law, the magnetic field is given by a mu0 over 4 pi. So that's sort of like our 1 over 4 pi epsilon naught from electricity. And then you have a source, IL, which is a vector, cross a unit vector. Now that so-called cross or vector product. I'll sometimes refer to it as one or the other cross product. And the analog to there is we had Q in the direction of R in the case of the electric field. And then that goes inversely as the square of the distance. This goes inversely as the square of the distance. So there is the same pattern. So that's for a little element of current of length L. So what you have is sort of a length L carrying a current I, and it will produce a magnetic field at a point B, that is r distance away. Now the tricky part is to find out what is the direction of B. And there we use, well, as I gave you 3 right-hand rules. The first of the right-hand rules is that you take the cross product of L with R. That means you point your fingers in the direction of L, you turn L into R, and you will get that B is into the blackboard, which we indicate by the tail of the arrow. That indicates which way it's going. So if I were in the blackboard, this in L, and I want to find the direction of the magnetic field at this point, I go L cross R, and B will be in that perpendicular direction. Or you can do a simpler rule, which is just put your thumb in the direction of, for this case, you put your thumb in the direction of the current, and your fingers will curl in the direction of B. So that B will go in this direction, and it will come out this direction. So you're going in and out, which is the same argument here. Suppose I have this, here's my R. I have L cross R, and you see over here it's coming out. So that is the pointy tip of the arrow. That's how we symbolize things coming in and out of the page. You've got to get used to this. It's this is a physicist saying hello with their magnetic personalities. Okay, so that tells us the direction of B around a current. And I have this slide where I compare just what I just did here for the point. What is the source of the fields? Well, in the case of electricity, it's Q. In the case of magnetism, it's a current element. That could be either IL or QV is the source. See, it's generating the field at that point. And now that's one way of getting things. The other way is we have these integral approaches. Like with Gauss, the Gauss theorem, we were able to solve some pretty hard problems, but very symmetrical. Very symmetrical problems you were able to solve with Gauss. And we have a similar but different law in the case of magnetism, which is called Ampere's law, whereas the Gauss law for electricity, you had a surface. And you had some charge, perhaps, inside. And you integrated the electric field over all the area of the surface. And that would tell you the charge enclosed, the net charge enclosed. In the case of magnetism, it's a similar integral kind of thing, but this is an integral over all the surface. This was called the flux. In the case of magnetism, what you have is currents causing magnetic effects. So what we do is we actually put a loop around the currents, a loop, a line. And you integrate the B along that line times the element of line. In other words, if you have a certain amount of B field here and a certain element of length, if you integrate B dot that length around the whole loop, you will get mu 0 I. You get the net current inside that loop. Now, one sort of passing idea, it's very, very interesting that in magnetism, we have this mu 0 constant, and in electricity, we have the epsilon 0 constant. And every case I've ever seen, if epsilon 0 is on the bottom, mu 0 will be on the top. Look at this one. Epsilon 0 is on the bottom, mu 0 is on the top. Every formula that I've ever seen, it goes that way. So it's another little clue. If you remember this one, this one is sort of the opposite. There's probably a deep reason for that, but we won't go into it. It's just helpful. Okay, but here you need to use this Ampere law as against Gauss' law. You, again, have to assign, just as we had to assign signs to the charge. You could have plus and minus, and they could cancel. And all it tells you is the net charge. So we have to figure out how to get the net current. And so you need a convention here. And that is right-hand rule number 2. And that is that you pick a direction around the loop with your fingers, and if the current line coming through the loop is going with your thumb, you call it plus. And if it happens that the current line going downward is around through the loop, you call that one minus. So in this case, if I make my loop this way, what is this one? This is a current that's going over. This one, this current is plus or minus. Oh, well, let's vote. Who says plus? Okay, who says minus? Okay, consensus is right. This one is a plus. How about this one? That would be minus. And this one would be plus. So the net here is this plus this minus this. That would be the net current through the loop. And that's how we do Ampere's law. And you'll see where, for some problems, again, like with the Gauss, you need a lot of symmetry so that you can guess, what do you really need to know? Well, you're trying to do an integral of the B along with a dot product along the line. So a dot product is big when the things are parallel, and it's 0 when they're perpendicular, because this is the cosine of the angle between. So when B is this way and dl is this way, you get B dot dl is just the values, dl. On the other hand, if you have B is one direction and L is in the other direction, then that is 0, because the cosine of 90 degrees is 0, so you get B dot dl is 0. So just as with Gauss's law, we look for loops that are either parallel to the B or perpendicular to the B. And then it makes life easy, because it's either B dot dl or 0. Just like with Gauss, we had these pillboxes. Like, for example, you had a surface, and if you knew the lines were this way, you picked a box where the surface was that way, or that way, or that way, or that way. So you find the lines are either parallel to the surface or perpendicular to the surface. And that makes the angles very easy. So here, what you want is you choose a loop that will be easy to handle by symmetry. Okay, and last time I went over how you do the cross product. We did it again here. And here are your three right-hand rules. The first is how you get the direction of B. That was the first one up here. As I, the current direction crossed with the distance. Or you can use your thumb and the curl of your fingers. The second one is how to go around an Amperian loop and just give signs to the currents going through. Or the third one we haven't got to yet is the direction of the force related to the direction of the current and the field that you're in. In any case, let's go on. So here's right-hand rule number one, yet again. And with a demo, we could show that the magnetic field, in fact, I showed it with a compass needle, and there was a current when I did the Ørsted thing, that the magnetic lines were circling. Very important idea, that circles the wire. And then you can use the Biot-Savart law very simply. If you have a circular loop, the heavy circle there is looked at at an angle, current going around that loop, and the question would be, can I find the magnetic field at the center of that loop? Well, it turns out to be, that's a very easy example of application of the Biot-Savart law. The reason is that you can find see, if you have this loop, and I want to find that the field B at the very center, I have current going around like this, and it has in a little length of it. But the current is producing a field, a dB here. Well, here's the. I'm going to use my magic trick of putting a piece of paper there, because I'm sure it's going to mess me up. Can I see my... This is pretty grim. Let me just try with this little piece of paper. See if I can move the arrow better. Good old capacity. Well, maybe it's a little better today. Okay, so here is your Biot-Savart law. You're getting each little element of current is producing a field at this point. So I have to add them all up. But see, I choose this very cleverly. I find dl parallel to di, tangent to the circle, so it's perpendicular to r. So this cross product of L, let's say dl cross r, but this is the tangent to a circle, so this angle is 90 degrees. So the sine of dl cross r is the sine of the angle. The angle is 90 degrees. It's the sine of 90, which is equal to 1. So for these right angle things, this is a great thing, because this is a right angle. I can just say that the dB is just mu over 4 pi I dl. Now cross r, this gives me just I dl, and this is a unit vector, so it doesn't do anything. So it's just a number now over r squared. Now r is, since this is at the center of the circle, let's call the radius of the circle a. The distance is a squared, and that's a constant. As I go around the loop, I'm going to integrate this around the loop, all the dl's and all the i's, but the i's and the dl's are parallel. The i's are always parallel to the loop, the dl's are parallel to the loop, and they're always perpendicular to the radius. Wherever I am, that is perpendicular to I and dl. So I end up with just mu 0 over 4 pi in fact, I comes out because that's a constant, and a square is a constant. So I just get the integral of going around that length, around the loop, from beginning to end. And that dl is the circumference of the circle. So I just put in 4 pi I over a squared, and the circumference of the circle is 2 pi times a. So the a's, one of the a's cancel here, and I end up with the field at the center as b mu 0 over 2 pi, let's see, what canceled here? The pi's cancel, the 2 cancels with the 4 to give me a 2, and the a cancels, so I have I and a. And that's it. But now also I have to say what direction it is. Anybody got any ideas what direction the B is here at the center? Coming out? Okay, very good. So I would put a dot here. I'm hearing things. Maybe that's a good sign. Because, okay, so the B is coming out of the loop. Okay, that's fine. That's the whole story. So, and by the way, it's different from the electric story. Because the electric story, as you recall, if I had a circular loop with charge on it, the electric field at the center was, by symmetry, 0. Because every charge produced a field in the plane in all directions, and so the net sum of all those electric fields was 0. So here, in fact, it's quite strong in the center. And you'll be using loops of wire carrying current to make magnetic fields. This is a common way. Coil, it's called a coil, magnetic coil. Okay, so now this problem could be expanded. And this is in the book now. This is an example in the book where it's made harder by saying, let me not find it at the center of the loop, right at the dead center, but how about along the axis of the loop? Let me go out along here from the center, but along the axis of the loop. Let me find the field here. It's really not that much harder, but now you've got another angle involved. And that's the example that's worked out in the book, one of the examples. Basically, it's the same idea, but you end up with, because of this angle, you end up with a field like this. And a piece of charge down here, or current down here, produces a field like that. So you have certain pieces of it cancel, and you end up with a difference. Well, we could expand on that. You have your loop of current. You have a pretty strong field in this direction. That one we calculated. If you do this other problem, it'll turn out that you get a field in that direction because the opposite sides cancel the ones sideways, and the field just sort of gets weaker as you go out. And the general picture is that the field goes out along here and comes back through here. That's the overall picture. We've done this part. The text shows you this part. The rest is rather more complicated because you're losing symmetry here. And you can't use symmetry to give the answer, but we can do it more sophisticated things. Now that looks vaguely similar to the electric case of something you have seen before, and that is an electric dipole, where way out here, you recall, you have your lines look like that. So we give this object a loop. We call that a magnetic dipole. Only because it has a similarity to the electric case. And it also has a similarity to a bar magnet, where, as we said before, if you have a north-south, The lines come out of the north, and we conventionally say they go in the south. So these two look analogous, and we would say that the directions in which that field is going, that's the north pole of this dipole. So it's north. I'm thinking the current is going, how did we do it? To try to make it more vivid, the loop is like this. The current is going this way. The B field is coming out this way and going around and coming back in. So it's sort of coming out of there. So we would call that the north pole of this loop. That's a little conventional thinking, but that's the way it goes. Do we get that? So that's a magnetic dipole caused by an electric current. And the magnitude of the dipole is given by, whereas the electric one, we just had D times E, and it went from minus to plus. That was our electric dipole. Here, the magnetic dipole, symbolized by mu, is given by the current times the area. That's interesting, actually. Now that I look at the similarity, see D times Q, see how you have a space, a thingy, a distance, and a charge. Here, let me even write it nicer, Q times D. So you have, instead of Q, you have I, and instead of D, you have A. So you have a dimension and a source, and here you have a dimension and a source for your magnetic dipole. And it's also a vector. And it's given by, if your current is in that direction, you use your right hand rule number 1 to say that the magnetic flux is going to come out of this. So that's your north side, and that's your south side. If the current, let me be clear on. Is that clear? Now I have a circle in this plane, and I'm going around there. So, and I put my thumb in the direction of the current, and the field is coming out. So that's your magnetic dipole. Okay, now time marches on. So as you see in my notes, a loop of current acts like a dipole. It has the same general feeling. You have a source, P, instead of P, you have mu. Interestingly, again, mu is on the top when epsilon's on the bottom. Notice those two formulas? Very nice. And it drops off as the distance cubed, both of them. So there's a lot of similarity there. Then we can do the same kind of thing we did here, but for a straight line. There's enough symmetry there to solve that problem by Biot-Savart. But once you got that, then you can prove the Ampere law. That is, if you go around a loop and enclose the currents within the loop, you will have all the currents with this convention that if the current is going with your fingers, then it's plus, whereas if the current is going opposite to your fingers, in the right-hand rule number 2, that's how you put a sign on the current flow. Here's an example. You can check yourself that you understand what that is. Now, the thing is that the actual Gauss law, integrating over a surface of B times its area, because there is no monopole, this integral is 0. You'll never catch a monopole inside, whereas you can catch electric poles or charges, that is to say. But how do we use B to find something, the actual Ampere's law, to actually solve a problem? And the most interesting problem actually is what's called a solenoid, which is a spool of wire carrying current. And that's a very common thing. The reason is that it's analogous to our favorite thing in electricity, which is the capacitor with its nice uniform electric field. This is the magnetic version of the capacitor, because it turns out that if you have a spool of wire, I like doing this. It goes like this, you see? This is fun. Like this, you're wrapped around like this, a cylinder, and you ask for the magnetic field inside. It's uniform throughout. So this is a favorite playground for problems. Solenoid. Now to use Gauss's law, Ampere law, you again just have to be smart in how you choose your loop. And you choose the loop by saying, now by symmetry, because all these wires are carrying current, their field is always, let's say the current is going this way, and I use my right-hand rule. Let's see. This is hard to do, isn't it? I need a cylinder. Imagine a cylinder, and my fingers go in the direction of, no, see, the currents are going this way, say. So you want to put your finger in the direction of the current, and your field will be in some direction like this. So you know, in general, the field will be parallel to the tube here, just because the currents going this way produce fields that way, right? That's your right-hand rule. So you have the field going that way. And because, let's say, it's infinite, there's no reason for it to bend one way or another, so they must be going straight. That's symmetry, as you use your symmetry, which you don't have all the time. Beautifully, you got it here. So they've got to go straight because there's no reason for them to go up or down. So if you put your loop, one of the lines this way, along B, then I put another line perpendicular to B, and another line perpendicular to B, and I go way up yonder where the field will be zero, say infinitely far away. I have a nice easy case, because I can just take my integral around the loop, B dot dl, and that should capture all the currents inside with mu zero in front. Okay, so by this clever choice of Ampere loop, this one, B dot dl, is zero. So let me perhaps do this. This is part of the circuit 1. This is, say, 2. So this, say, is 3. And this part of the loop is 4. This is a line. So my integral is B dot, let's say this length here is L. B dot L for piece 1. Now B dot L, this is just BL because they're parallel. Now this one is perpendicular, so B dot L is 0 because they're perpendicular. The cosine of the angle is 0. Oh, this one too. Now I do 3, but here B is 0 because I've gone infinitely far away. So B dot L is also 0. And if I do part, that's 3. And then if I do part 4, they're perpendicular. B dot L is 0 because they're perpendicular in here. So you end up, none of these contribute. You get B dot L is equal to mu 0 I. Now what is I? Well, I have a lot of lines, a lot of wires coming through here. Let's say I have n wires per unit length. So actually I've trapped in there, the current is n there are n, let's say n wires in the length L. So my B dot L is equal to mu 0 I times the number of wires that I've trapped. So I get the answer, B is mu 0 I n over L. And that is called the line density in a way. This is a density of lines, of wires per unit length. So that's the answer for the uniform field. You see, it didn't matter where I put this line here. So B here is B here, same here. So that tells you that the field is uniform throughout that solenoid. So that's an application of the Ampere law, and the reason I could do it is because I had enough symmetry to say something. Okay. Let's see. How much time do I have? Zip. The other law that you need to know, and that is, all right, so up till now what we've done is, that's probably mine. The other thing that we need to know is, these are ways of calculating the B field. But now, once you've got the B field, what is the force? And that is where you use the right-hand rule number 3. Force is equal to Q, the charge that's moving, V cross B, or, again, this is the magnetic charge, or I, L cross B. This is a unit length of current flowing. Now, I like to write that myself. It's easy to remember as LIB because it reminds you of women's lib, and that gives you force. So I write it that way. And it's a cross product. So the point is that if you have a flow of current, let's see, does this light up? Yeah. That is an electron flow that you can see. And here is a North Pole, and there's a South Pole. We checked that before. And so the field is going from north to south. It's going bulging out, but between here, it's probably pretty straight. And so I'm going to put a field this way. The electrons are flowing. See, there's a charge, a plate there. So the electrons are going from here to here. And let's see. See, the V is this way, B is that way, the force is that way. That's the tough part about magnetism. It's the right angle stuff. Now, if I turn it around, in principle, the field is this way, the current is that way, it should go down. So I can steer the beam. This is a way TV sets used to work. They had both electric steering, like go through a capacitor. We did that in class, the jet thing. And you could steer also with magnetic fields, because if you turn the magnetic field on and off with a current, you could steer the beam across a sheet, across a face of the tube. Okay, so that is one application. The other is, if I put current through this loop, I've created a magnetic dipole. And if I have a dipole near a magnetic field, it will turn. See, I can do funny things like this. Now, the trick is I can make a motor if, when the current comes in, this gets attracted because there's a current flowing, it gets attracted to one side, but it would stay there. So what I have to do when it comes to one side, I have to switch the current so that the dipole changes its direction, and then it'll keep going, hopefully. So let's see, am I turned on here? Okay, so what's doing, it's switching. I turn the current off, guys. You can slow down. It's not much friction there. So the point is, let me explain briefly what this thing is doing. If you, I hope you can see this. You see there's a thing here, which is a metal conductor. Did I turn that off? That's pretty hot. There's a metal conductor here and a metal conductor here. When you go around, the contact touches one and brings current in one direction. Then there's an open space. And then the current goes to this side. It switches the direction. It's very smart. It switches the direction so that the dipole gets continually pushed in the same direction. You think about it, you'll see that that's how that works. And these So this is how your electric motor works, where you put current in a coil, you create a dipole. The dipole is attracted to this side, but when it gets here, you don't want it to stay. You switch the current, so the dipole now is repelled from that side. We'll maybe go over that in some detail next time. Okay, thank you.